Beleza? Então eu vou chamar o Chair, que vai apresentar o nosso próximo plenarista. Obrigado, Yuri.
Hello everyone. I think this is going to be recorded, so I will speak in English so that anyone watching the video later on can appreciate that. So it is a great pleasure and honor to introduce you to the speaker of this morning, the mechanics session, Gabriel Gatica from the University of Concepción in Chile. So I was telling him on the way that I phoned the Chilean police service and I got all the details about his life here in hand, so I'm going to list some to you so that you know our speaker a little bit better. So Gabriel graduated in mathematics in 1980 at the University of Concepción, and later on went on to get the degree of mathematics engineering at the same university, where he also got his master's degree. And then he went on to get his PhD at the University of Delaware at the United States in 1989. He then became a full professor in numerical analysis of partial differential equations at the University of Concepción in Chile. And he did a great job there, founding what is today the CIMA, Centro de Investigación en Ingeniería Matemática. Yes, and that's it, right? So he has been associate editor of several journals. I managed to count 6, one of which was the SIAM Journal of Numerical Analysis, which is the most prestigious journal in the area. He has supervised around 20 PhD students and 30 other students in undergrad and master's theses. He has been, of course, invited speaker in several international conferences. And of course, this is the most important one he has ever been. So he's now increasing his CV on that matter. And he's interested in showing his research areas are existence and unicity of continuous and discrete solutions of partial differential equations, providing a priori and a posteriori error bounds for numerical schemes. He's also interested in fully discrete methods and the implementation of efficient computational algorithms in problems involving fluid dynamics, as he's going to tell us today, solid mechanics, electromagnetism, and of course potential theory. So I'd like to welcome Gabriel. Thank you so much for coming, Gabriel. It is a great honor to have you here. Thank you.
Thank you for, first of all, for the invitation and for this very fake introduction. So thank you all for coming. A very nice city, actually. I was telling Yuri, this is my first time in Brazil. My first time in a, well, I was in the airport, but that doesn't count. And it's very, very beautiful to see so many green areas all around the city. So it's very impressive. So I'm enjoying this stay. All right, what I want to, not working. All right. This is a joint work with several people from Concepción, from other places, undergrad student, PhD student, and collaborators. So the main idea of the talk is to show some aspect, not all of them, because there is no much time, of the analysis of nonlinear and some coupled nonlinear problems in fluid mechanics by means of Banach spaces, mixed formulations. So in order to do that, I will refer briefly to 3 different model problems: the coupled Darcy and heat equations, the Navier-Stokes Brinkman problem, and the chemotaxis Navier-Stokes problem. So let me begin with some preliminaries. Just basic things to remember what the Vega space is, right? The measurable functions with the power t bounded, the usual Holder inequality relating the s and the t conjugate, so you get this inequality that the integral of v times w is less than or equal to the norm of b ls times the norm of w lt. And certainly the particular case that you have a t equal s equal 2, you have the well-known Cauchy-Schwarz inequality. In addition, we are going to use some concept related to solvable spaces, in particular H1, which are the distributions in L2 whose gradient is also in L2 vector, H div R, which are the vectors in L2 whose divergence in the distributional sense it's also in it's in LR. R is greater than 2n divided by n plus 2, and that the reason of that something I'm going to say next. And also we remember what W1S is, the distributions in LS with gradient in LS as well. And then HT div T, which are the tensors in the vectors in LT with divergence in LT, again in the distributional sense. All right. These are very common spaces, particular this one and this one here. For the weak formulations, I'm going to discuss in the next sections. So the reason for this R greater than 2n n plus 2 is because of this integration by part formula that hold in those cases. It has to do with the fact that H1 is included continuously in LT for any t greater than or equal to 1, but only in R2. In R3, it becomes 2n divided by n plus 2, 6/5. That's because of an embedding of solvable spaces. And then you have this integration by part formula relating a vector function in H div R with a scalar function in H1. Then when you extend this to the more general case, Ht div T, then you have a similar integration by part formula, but holding now for tau in Ht div T and a b in W1S. And that reason, right, because for instance, to understand this expression, you need that if this is in LT, then the gradient needs to be in LS. So this expression is bounded because that's given by the Holder inequality. It doesn't explain that the B is taken in W1S and the tau in that space. Similarly, explanation for that. So those integration by part formula are key formulas in the derivation of our weak formulations, what I'm going to explain for the three examples. The details of each model are going to be decreasing because of time. I will spend more time in the first model and then less time in the other two, all right? So the first model is the coupled Darcy and heat equation. It has to do with the distribution of the temperature of a fluid in a porous medium. That's the reason you have the Darcy equation here with incompressibility for velocity, U is velocity, P is the pressure, and a Neumann condition, a normal component of the velocity equals 0 on gamma. And that is coupled with the heat equation, which is a convection diffusion equation, which depends on the velocity coming from Darcy. Similarly, the viscosity in the Darcy problem depends on the temperature coming from this equation. So that's why it is a couple heat and Darcy equation. So here the notation that we're using, use velocity of the fluid, P is the pressure, bar phi the temperature, U is viscosity, K is thermal conductivity, and F, boldface F and F are external forces acting for each model. So the interesting part of the model is the fact that they are a couple. Otherwise, you can solve this independent of that, right? But then here you need the velocity coming from that equation. So since I'm interested in mixed formulation, I should have said this before, mixed formulation has to do with the fact that you introduce, in addition to the original formulations of the problem, you introduce other unknowns depending on that, or depending on the integration by part formula, or depending on some physical interest. For instance, if you're dealing with the heat equation, certainly you're interested in the temperature, but you may also be interested in the gradient of temperature. If you are dealing with an elasticity problem, you are interested in the displacement, but you might also be interested in the stress. And the stress is a new variable introduced in the formulation. As well, you might be interested in the flux, in the traction in that problem, all right? So mixed, in my concept, means introducing further unknown depending on the original unknowns, but also depending on some physical behavior. So that's the reason I'm introducing here what we call the pseudo heat flux, which is this sigma equal k gradient of bar phi minus phi times u. And because of the incompressibility condition, when you take divergence of that, phi, bar phi times u, you just get the convective part. And of course, if you take the divergence of that, you obtain the Laplacian. So the equation then can be written, instead of reading it in this way, as a second order equation, you just write it in a first order by introducing this auxiliary noun sigma. So you get the divergence of sigma equal that, and then your system, now your coupled system, can be written in this way. Darcy is still the same. We haven't done anything there. Actually, Darcy is already written in mixed form because the velocity is expressed in terms of the gradient of pressure, right? But now the heat equation, as you can see, is of first order because we introduce this sigma equal to this, and then you get the equation itself, the equilibrium equation or momentum equation, I think, is divergence of sigma equal minus f. All right? That's the main ingredient of doing mixed formulation, is introducing this further unknown. One advantage, and among many others, but one advantage that one might obtain by doing this is the fact that because of this variable sigma here, one could obtain the gradient of the temperature in terms of this new unknown sigma and the bar 5 and u. So that means that you don't need to make any numerical differentiation to obtain an approximation for the gradient of temperature. So that's one advantage of using this mixed scheme. Then you test against tau in order to get the fully mixed formulation. We test what we will call now the constitutive equation, which is going to be that. So we test this against tau in the same space where sigma is going to be looked for. So you obtain that, and we are going now to see two things: how to integrate that piece and what is the meaning of that. So then is when the Cauchy-Schwarz and Holder's inequality come into play, because then you observe that in order for this to be bounded, in order for this integral make sense, because of Holder, first Cauchy-Schwarz inequality and then Holder, you get that this is bounded by the norm of phi in L2 L and U in L2 J and the L2 in tau. All right? So that means that initially we are going to look for bar phi in the L2L space, U in L2J and tau in L2. And again, for this first term, we observe, because of Cauchy-Schwarz, that we need sigma in L2 and initially gradient of bar 5 in L2. But then we apply one of the integration by part formula that I wrote in the preliminary section. So we integrate by part this, and then we obtain integrate by part this piece, so we obtain that. And because of the boundary condition for bar 5, which is chosen to be 0 for simplicity, and then you obtain this is minus phi divergence of tau. So while in the beginning we assume that gradient of phi is in L2, that means 5 in H1. However, after integrating by part, we realize that actually we don't need to look for bar phi in that space, but still only in that one over here, L2 2 L. But then, for this expression to make sense, you need then the divergence of tau be in L, the conjugate of 2L, all right, because of Holder. Therefore, that's what I'm saying here. The divergence of tau is in the conjugate to L prime conjugate of 2L. And then this is another reason, again, because you need that H1 be included there, so that imposes this inequality that we wrote at the beginning. And because of the existence of solution for a Neumann problem that I'm not writing it here, but that we need for the analysis, it is a Neumann problem where you look for a solution in W1S, and that Neumann problem, in order for it to have solution, you need some restrictions on the indexes. So 2j less than or equal to 4 for n equal 2, and 2j less than or equal to 3 for n equals 3. So when you play with the indexes, so finally you arrive to the feasible indexes that you can, the feasible range of the indexes that you can choose for your problem. If it is 2D, we have a range for each one of the indices that we are going to use. Rho is to L, bar rho is the conjugate of that, R is to J, and S is the conjugate of R. So we obtain, this is a bit just algebraic manipulation, you get some ranges for those exponents. And surprisingly, for 3D, you just get one possible choice. And this is obtained in several other examples, but it is not a general rule because there are other examples where you do have ranges also in 3D. So don't get enthusiastic that we are going to have this in all cases. This is just for this case. So then we are looking for solution bar phi in L rho u in L r and tau in h d bar r. Remember that the variance of tau has to be looked in L to L conjugate, and to L conjugate is what we have called bar rho. All right? So those are our spaces. In this way, the first equation now, I'm looking here for the wave formulation for the heat equation. The first equation becomes this equation here, which you look for sigma, right, and bar phi, so define this for all tau in that space. And then you also have the equilibrium equation, the divergence of sigma equals something, so then that is tested. Since the tau is already here, it makes sense to look for the sigma in the same space. So that means that the divergence of sigma is going to be in L bar rho, and therefore the psi testing it is going to be in L rho, which is the conjugate of bar rho. All right, again, Hölder inequality here. So finally, you arrive to the mixed formulation for the heat equation, in which, given the velocity, then you look for sigma in that space and bar phi in that space, satisfying these two equations here. And I have written in red this because this can be seen as a perturbation of the problem, including A, B, and B. And this is the classical structure of mixed formulations in what people call the babushka-breathy theory, that they have this form, A, B, and B. When A is symmetric, we are not assuming symmetry here. In the particular case, it is symmetric, but in general, it might not be. But if A is symmetric, then the solution of a problem involving A, B, and B, in this way, forget about that for a moment. The solution of that problem corresponds to a saddle point problem of a functional defined in terms of A and B. So that's the reason why we used to call all the problems involving this structure saddle point problem, even if they are not saddle point, right? And for the Banach spaces, we still call them saddle point problem. But be aware that that's only true in the Hilbert case and when A is symmetric, all right? Okay, then knowing that the U has to be in LR for the heat equation makes sense, then when we look now to the Darcy equation, okay, we know already that, and that is a constraint. So therefore, when we test this equation, we have to make it so that the testing, it's allowed. And therefore, since this viscosity, I didn't write it, but say now this viscosity is assumed to be bounded on smooth. So basically, for when we test this, if U is going to be in LR, so we need to test with something in LS, with S the conjugate of R, all right? And because of this condition here, the divergence of U equals 0, I mean, on the boundary condition, which was this normal component equals 0, so then we introduce this space X2, which is what we call H0 R div R, the vectors in HR div R with normal component 0, and then the test is going to hold with this X1, which are the function in HS div S with a normal component equal 0. So everything makes sense. Now if we test this equation against a B in X1, so we get GAT, and then this gradient of P times the B, the integration by part, we use the second one that I mentioned before, all right? And that gives rise to this integral of over omega of P times the divergence of B. So that's our first equation, and as you can see, the U is going to be in HR div R with normal component 0, and the B is in HS div S with normal component 0, and R and S are conjugate to each other, all right? And then, sorry, then compressibility condition, since the U has a divergence in LR, so we tested again a Q in LS. And that is the second equation is going to be integral of Q times divergence of U. It's going to have the same expression like this, the same algebraic expression, but they're holding in different spaces. One involving HR div R with LS, and the other involving HS div S times LR, all right? And another technical issue, because of the uniqueness for the pressure, because if the pressure is constant, this vanishes. So in order to have a unique pressure, we introduce then the space for P in those P in LR with mean value 0. And similarly, the test function Q is going to be in LS with mean value 0. So finally, we arrive to this, again, saddle point problem. It's not a saddle point, but we used to call it that way, in which given bar 5, now you look for U and P in those spaces X2 times M1, such that this equation is satisfied for all B in S1 and for all Q in M2. And this is the more general case that you can find in Banach spaces for a typical saddle point problem, in which the bilinear for B1 and B2 are different. Remember, in the other case, they were the same. These are different. So summarizing, we have then our couple problem with the two equations for the heat equation for Darcy. Here we have the typical structure of the saddle point with the same B, and here we have the more general one with B1 and B2 different, although they are algebraically the same. P times divergence. All right, pressure times divergence, but they are acting on different spaces. So because of the couple structure of this, we propose a fixed point strategy. So first we define the operator that given a bar phi, you define the solution of that, and then the other operator that given the U, you define the solution of that, all right? So those are the operator T tilde acting from L rho into H0 R div R, so that to each psi assigns T tilde of psi equal U tilde, where U tilde time comma P tilde is the solution of this generalized saddle point problem. And similarly, now we define the operator hat T that given a velocity assigns the solution of this problem here, in which you have the typical saddle point structure. So it's very easy to see then that the whole coupled problem can be written as a fixed point equation in terms of the T tilde and hat T, which is given by this T operator given by T tilde of hat T of W. So solving the coupled problem can be seen to be equivalent to find a fixed point of the operator T. I'm not going to spend time in explaining all the ideas behind the way this fixed point theory is handled, but I'm going to concentrate in the existence of solution for each one of the decoupled problems, the decoupled ones, all right? So first, the well-posedness of the operator defined by the tilde, and here the key issues are that when you have a bilinear form A, and this tilde is the one here, right? In order for this, the main theorem says that you need basically that the operator induced by B1 be surjective, that the operator induced by B2 be surjective, and that the operator induced by this bilinear form be bijective, but in the kernel of either one. Basically, that's it. When B is the same, it's easier. You need that the operator induced by this bilinear form be surjective, and the operator induced by this bilinear form be bijective in the kernel of that operator B. All right. So that means that then, in order to prove that, one had to show this what we call in subconditions, which means that you have to prove that given a W in the here K1 and K2 are the kernels of each bilinear form, the kernel of B1, the kernel of B2, all right? And it turns out to be those functions in that space with free divergence, in each case, both in different spaces, but with free divergence. So then we need here to show that this supremum, given a W in K2, the supremum over the other kernel has to be bounded by a constant time the norm of W, all right? So if we look at that expression here, is the integral of mu times W times B. Think of the easy case, which is the L2 case, which is Hilbert. If it is Hilbert, this is very easy, because then when you bound, when you want to get a lower bound for this, okay, you choose, given the W, you choose the B equal the same to the W. Forget for a moment for this mu, because it is bounded, all right? So let's think that we have integral over omega of W times B. In the Hilbert case, L2, given the W, you can take B equal W, and then you get the norm of W squared in the top, and here you got the norm of W in this part, and therefore the equation of that gives you the norm of W, so then you have the proof with alpha tilde equal 1. Right, that's in the Hilbert case. But we are not in the Hilbert case because the spaces where this is acting are different, right? We are K1 and K2, so we have to make a proper choice in order to bound this and obtain that. We have to make a proper choice for the B that we are going to take here in K1. And that has to do with what I mentioned before. We are going to use the well-posedness of a Neumann problem in which you have certain restrictions for the indexes, and that Neumann problem allows to define an operator ds going from Ls into Ls, which has this property here, that is free divergence, and that normal component equals 0. So then what we do is, given a W in LR, this is well known, you define the function modulus of W to the power R minus 2 times W, and that's very easy to prove that this Ws is belonging to Ls. Given now that Ws, you put it here, and then you take the operator ds of that Ws. This is what I'm saying here. So taking, in order to bound this, we bound it below by choosing a particular B, any one. And the convenient one here is this one here. Taking B equal ds of that Ws. And this operator here, as in addition to this property, has this property here, that the integral of W times ds of Ws is equal to the integral of just the product of W and Ws. And that's also very well known that when you do that, then you get the product of the norms of W and the norm of Ws, all right? And when you pick that B equal that operator is bounded, so therefore the norm of that x1 is less than or equal the norm of ds. So, but the reciprocal of that, 1 over that, is greater than or equal 1 over that norm. So then you get that the constant alpha tilde is precisely the reciprocal of the norm of the S, because then, right, you have that, the product, and then below you have the WS again, so you get the inequality with that constant alpha. It's a bit technical, but what I'm what I'm trying to emphasize is that the choice in doing this, which in the Hilbert case will be very easy, in this case we have to go through an auxiliary operator which has to do with a Neumann problem whose existence of solution is restricted to certain ranges of the indexes. All right, that's what I want to show. So, and then I was saying that the main theorem requires that that M sub condition for A and also M sub condition for B1 and B2, and that means that the operator induced by B1 and B2, they need to be surjective. And being, and being surjective is equivalent to asking that the adjoint of them be injective and of closed range. The students on my short course, they should know this. I was telling about this all along the week. So, anyway, so therefore, I'm proving then the M sub condition for BI equivalent to prove that the operator induced by that, the adjoint of it is injective and of closed range. And that is equivalent to show this inequality over here. And this, I'm not giving any detail, but it can be proved by using another auxiliary problem in which the data of that auxiliary problem is the given Q that we take here, all right? So finally, one is able then to prove, according to that, the well posings of the operator T tilde. How much time left do I have? We started at what time? 25 minutes, okay. So now relax a bit. All right. Is it too boring? No? No? Are you sure? Carlos? Is that Carlos? No. Carlos, it's okay? No? Complain to Yuri. All right. So, in order to prove now that the operator induced by hat T is well posed, it's very similar and even easier, because in this case, I also mentioned this in my short course yesterday. This A is elliptic in this particular case, because the AT in that space, because the kernel now is again free divergence, and A is again the A of tau and tau is the norm of tau squared, and when that holds, that we call elliptic. So the M sub condition for A is very straightforward to be obtained. And then for the for the bilinear form B, again we have to prove an M sub condition, and similar to that one, that goes through the solution of an auxiliary problem in which the data is the given psi over here. So it's also able to prove that. Then, having proved that both the coupled problems are well posed, what we do now is, in the particular case of the heat equation, we just plug all the bilinear forms into just one. And here it comes the fact that when you prove that you satisfy the Babushka-Bressi theorem, which is we just mentioned, that is equivalent to verify the hypothesis of the well-known Lax-Milgram lemma for the whole operator, for the whole bilinear form, if you add both equations. So what Babushka-Bressi does is that because of the structure of A, B, and B, it's not straightforward to prove that the whole bilinear form is going to satisfy the M sub condition which is required by the Lax-Milgram lemma. So Babushka-Bressi gives a better way of doing that, which is proving that B is surjective and that A is bijective. The M sub condition for B, the M sub condition for A. So then, because of finally the things are equivalent, we have actually the the global M sub condition for A, and that means this inequality here. So but we had a perturbation of our problem. So then we define this a new bilinear form, which is including the perturbation. And then it's easy to show that for a sufficiently small velocity, which means this inequality here, this operator, this bilinear form AW satisfies the hypothesis of the Lax-Brinkman lemma, and therefore the whole problem involving the perturbation is well posed, but under a restriction on the given velocity. So this is not going to work for large velocity. All right, so further remark concerning this model, one can prove that the operators T and T tilde and Ht are Lipschitz continuum, and therefore the whole operator T is Lipschitz continuum. That's very easy to see. One applies the Banach fixed point theorem for the continuous case. But in numeric analysis, we are also interested in the case in which we consider the same problem, but instead of looking at the continuous space, we look at finite dimensional spaces. So we look for an approximation that we call the Galerkin method, the Galerkin scheme. When you choose those finite dimensional spaces as piecewise polynomials, that's what we call the finite element space, finite element method. All right? And in this particular case, we use what they call the Rabier-Thomas spaces, in which we approximate locally on each triangle of the domain, we approximate the sigma, the pseudo heat, by a vector polynomial of degree k plus the vector x times a scalar polynomial of degree k. That is the usual form of a Rabier-Thomas spaces. And it is shown that with that kind of spaces, the scheme is stable. That means that they have solution, unique solution, and it depends continuously on the data. So now, when you go to verify now the Babushka-Bressy theorem for this discrete case, so you're going to do the same in the sense of proving bilinear form B satisfy the IMSAP condition, but now with the finite element, with the finite dimensional spaces. So now everything is discrete. And in that case, we require that the constant involved be independent of the dimension of the finite element subspaces, because the idea is that that dimension is going to increase. So in that case, one has this discrete kernel of B1 and B2, and then in order to follow basically the same idea, here I'm explaining that, the same idea when we try to prove that IMSAP condition for A, I cannot take just ds of WSH, even if the WH that I'm taking originally is in the finite dimensional space. When I apply to it the WH, comma S, so that it becomes in LS, and then I apply the operator ds, that's going to be in LS, but it's not going to be necessarily in my finite dimensional space. And that's why, in addition to that, when I'm trying to explain the same idea that we just did for the continuous IMSAP condition, all right? Choosing, in that case, given a W, we just choose to get the lower bound of the supremum, taking the S of that W. But that doesn't work in the discrete case, because the ds of that is not going to be in the discrete space, all right? And that's why we need to project. This is the projection. The orthogonal projection in L1 to KHK, this orthogonal, of course, is between, because, of course, here we don't have in a product. But the definition of that projector is exactly as if it was the L2 orthogonal projector, the same definition. Okay, so in order for the same argument from the continuous case to work in the discrete case, the first thing we needed to do is to define this projector. And actually, we found out that it was the first time this was going to use in this context, and that projector, the bounded, the fact that this is bounded wasn't proved. And we were able to prove it only in 2D. So in 3D, proving that this projector is uniformly bounded in the LS norm, I'm talking the LP norm, LR norm. In L2 is trivial. In L2 it's certainly bounded. But in LR, it wasn't known to be bounded, and we were able to prove that it was bounded, but only in 2D. So there is a technical difficulty in 3D. So in that, we were able then to prove the subcondition, the discrete subcondition for A, and following another argument, we were able to prove the discrete subcondition for BI. In the case in which omega is not convex, which is also included in our analysis, we need an extra regularity for Neumann problem, and that adds another restriction for the indexes in which we are going to look for the unknowns. And in this case, certainly, we apply the Brouwer and Banach theorem, first for existence, and that for uniqueness, Brouwer for existence, and Banach for uniqueness. All the details can be found in this paper recently published in the IMA Journal of Numerical Analysis. So that's all what I'm going to say about the first model. The second model is what we call the Navier-Stokes Brinkman problem. It has to do with the modeling of a viscous fluid within a porous medium. It's basically Navier-Stokes plus a zero-order term here. All right? This is not coupled, but it's still nonlinear because of that. Incompressibility condition, Dirichlet condition for velocity, and this condition for the uniqueness of the pressure. All right, a very, very simple, very well-known problem. So U velocity, P the pressure, E of U is the symmetric part of the gradient, also called strain rate, the strain rate tensor. Eta is the scale inverse permeability of the porous media. For me, it's a constant. Don't ask me what it means. That means exactly. Lambda, the inverse of Riemann numbers, the same comment. Mu, the viscosity, okay, constant. F, external force. U, Dirichlet data, incompressibility condition. Because of that, well, you need a restriction on the Dirichlet data. It has to satisfy this condition. And here we need to use the deviatoric tensor, which is making a tensor with trace equals 0. So just subtract 1/n, the trace of the tensor times the identity. All right? So that's the setting for this Navier-Stokes Brinkman problem. So in this case, again, we are doing mixed formulations. We like to introduce further unknowns of interest, and then we are introducing the strain tensor as an unknown, which is the gradient minus gamma, and gamma is the vorticity, the skew symmetric part of the gradient of velocity. So in doing that's first unknown. And then we also introduce the stress tensor, in this case, which is lambda mu t minus u times u minus p times the identity tensor. In that way, our Navier-Stokes Brinkman equation can be written very simply in this way because of that definition. So we have that, and we take the deviatoric tensor to that, and the deviatoric tensor of the identity is 0. So we just get this. The deviatoric of this is the same t because the trace of t equals 0 because of the compressibility condition. All right? And we get that. And you can take now the trace of that, the trace, metric trace of sigma, and then you obtain a formula for P, because here you will get NP, so the trace, P can be obtained in terms of sigma and U in this way, because the trace of that is 0 because of the incompressibility condition. So you are able to obtain the pressure in terms of sigma and the velocity. That's another advantage of this mixed formulation, that you obtain an expression for the pressure, so you can eliminate the pressure for your formulation. So in this way, we reformulate the model T plus gamma equal gradient of U. This is the now the constitutive equation. This is the momentum equation, and this is a condition now, the uniqueness condition on P was mean value of P equals 0. Now it is transformed in the mean value of the trace of sigma plus U times U. All right? And there is the condition. And here, I think I'm going to rush a bit. And here we integrate by part. Again, testing against tau, you get that. And now the integration by part of this, according to the formula, we assume that in order to apply our integration by part formula. So that remains the same. And this becomes minus U times the divergence of tau. So we are going to look for T in L2, gamma in L2, and U in LR prime, where R prime is a conjugate of R, and this tau is in H deep R. That's initially, all right? and T, which is the strain rate tensor, because of the compressibility condition, the trace of it is 0, so we look for that in that space here. The tensors in L2 with null trace, and gamma, which is the vorticity, which is skew symmetric, so we look for it in the L2 space with skew symmetry. All right. So then testing again S, the constitutive equation, we get that. And this term here, so we apply Cauchy-Schwarz-Platzholder, and when we do that, so we get U in L2L, U in L2J, and S in L2. But of course, this U is the same, so of course that means that U is in the intersection of that, so finally we take L equal G equal 2. That means that we are going to look for U in L4. So R prime is 4, and that means then that the conjugate of R prime, which is R, is for thirds, so that means that the space H div R becomes H div for thirds, all right, with now a specific index. And testing again L4, the momentum equation, you get this here. And here we have an interesting thing, well, and then the symmetry of sigma is tested again the skew symmetric. That's very well known, right, that a tensor is symmetric if and only if it's orthogonal to the skew symmetric tensor. So that's what we are imposing here. And for the analysis, we just use a decomposition of this H div as H0 div plus the multiples of the identity. And this H0 div are those tensors with mean value 0 for the trace. All right, that's another technical reason to do that. So after all, we arrive then at this formulation here. These spaces for vector T, which involve T and sigma, and vector U, which involve U and gamma. So we have this structure here. And I've written in red this because, as you can see, all this piece in red has the saddle point structure in the general case, with B1 different from B2, because acting on different spaces. But if I put together all these red bilinear forms, it's just one bilinear form, which I'm doing here. Well, here is the definition of each of the bilinear form over there. So if I put together A, B1, and B2 in just one boldface A, we arrive to this. And this is what this structure here now, in which this has a saddle point structure, but now together with that B and that C, it's what we call a perturbed saddle point problem. Why perturbed? Because of this C over here. That's the perturbation. Because if we had only this piece here up to here, that would be just the usual saddle point. But because of that, it's perturbed. And surprisingly, for this kind of structure, in the Hilbert case, it was well known, the theorem. But in the Banach's case, it wasn't known, and so that's something that we had to do. And we were able to prove then a theorem, which is in this paper, with, by the way, with an undergrad student. He was an undergrad student, and we proved the theorem that says that if the bilinear form A satisfies the if sub condition with respect to the first component and the if sub condition with respect to the first component, those two conditions, what they are saying in the kernel of B, okay, in the kernel of B, those two conditions are saying again that the operator induced by this is bijective in the kernel of B. And if B satisfies this in sub condition, that is saying that the operator induced by B is surjective. So basically are the same conditions of the non-perturbed case, all right? But you need, in addition, that A and C be positive semi-definite and that C be symmetric. So this only works in the case that H, we have here H and Q, and also H and Q, all right? Same spaces. Corresponding assumptions on A, B1, and B2, which correspond to the general Babushka-Breathitt theory, which I referred to that classical paper from 1988 that was made that for the A, B1, B2. I use a fixed point strategy. Again, we arrive again to this, so we look for the operator that given a W, we put a W here, so we solve this linear problem where this is seen like a perturbation, and we analyze this with the theory of our theorem concerning perturbed saddle point problem. So the Navier-Stokes Brinkman equation then can be written as a fixed point equation in this way, and all the details are found in this paper, which is going to appear soon. And this is another undergraduate student, and this is a collaborator from Monash University in Australia. I got 5 more minutes. All right, this is going to be fast. No, I can tell a joke. You choose. Bolsonaro, Boris, Lula. All them. Well, the joke is always the same. It's only the changes of the story. Okay, be serious now. Okay, the chemotaxis Navier-Stokes problem is a model, I've been told. It has to do with the cell movement driven by a chemical signal within a fluid. Basically, it's a Navier-Stokes equation which depends on the cell concentration in some fluid, plus a convection diffusion equation of that cell, which depends on the velocity, but also depends on the concentration of the chemical signal, and a similar equation for the chemical signal. Okay, so 3 equations coupled with Dirichlet boundary condition. I'm not going to explain all the detail, but okay, here we have velocity, pressure, cell density, chemical signal concentration, fluid viscosity and density, diffusion coefficient of each case, consumption rate for the chemotaxis of U and gamma, and so on, and certain data, source function, and the Dirichlet data. Again, mixed method, we introduced the velocity gradient as a new unknown, and we introduce a kind of what we call a Bernoulli type stress tensor as an auxiliary noun, which is this sigma over here. In that way, our first equation, the Navier-Stokes type equation, can be written in this way, with again the pressure expressed explicitly in terms of sigma and U. And because of the uniqueness for the pressure, we need this condition for that term over there. For the cell and the chemical equation, we do similarly. We introduce the solid stress for the cell and the chemical concentration gradient as a further unknown, so that those equations can be written in this equilibrium form for the cell concentration and for the chemical concentration. So finally, okay, this is the reformulation of the model in mixed form. All the equation for the Navier-Stokes type equation, all the equation for the cell concentrations, and all the equation for these 2 equations for the chemical signal concentration. And nouns and spaces, we do formulation, and here there is a novelty with respect to what we were doing in the other 2 examples, that now in our analysis necessarily has to appear this space HR, not div R. That's what we had before. We got into HR div J with R greater than or equal to J. So at first sight, we thought, okay, this is not going to work. But then, thanks to some embedding of solvability spaces again, the im subcondition and so on could work similarly as done in the other cases. So we went through it. So, and this is the other spaces for the other unknowns, HS div S, LR, and LL. And again, in this case, because of technical reasons, for the L2, for the 2D case, we have ranges for J and L, but for the 3D case, you will have only one possible choice. So one possible choice where you can look for the unknown. So the final structure of the problem is this one here. This is for the Navier-Stokes type equation. When you are given a U, for instance a W, then this becomes linear. So then this becomes an A tilde with this and that is a typical structure of the saddle point problem. This is already a typical structure of a saddle point problem, and here we have the more general one in which B1 is different from B2. And all the other terms are perturbation that depends on the other unknown. So this term here explains the coupling, and this one here explains the coupling between the three equations. So that means that we define suitable operators, and then we define a fixed point operator to write a fixed point equation. So here are some technical comment. As when you fix B and B here, this U equal that one, then that becomes 0, and that this in subcondition, I will just mention that in the case of HR div J, this in subcondition, it's possible to prove it similarly as we did it in the other case, but because of this embedding of W1J continuously into LR, okay, that was possible. So fixed point strategy, and this is in another paper which is recently submitted with some collaborator, and this is a PhD student recently. So in order for you to believe me that we have made all numerical experiment in all three examples, I'm just showing just a short example here of the chemotaxis case in which you have, here we add the time variable, so we are able to show 3 different times. We have a concentration of cell here, a concentration of chemical signal here at some time, a second time, a third time, and you can see that the cell is attracted by the chemical, and finally they are all disappears somehow. All right, or merge. So computed magnitude, velocity, cell density field, and chemical signal concentration field are 3 sequential times. Finally, concluding remarks. In all this mixed formulation and many others, the choice of spaces strongly depend on the kind of non-linearities involved. Second, existence and regulators of solution and PDEs play key roles in our analysis for the in-sub condition and so on. Injection between solid spaces come also into play. Saddle point and perturbed saddle point problems in Banach spaces among the resulting formulations. Brouwer, Banach, and Schroeder fixed point theorems are applied. Numerical experiment are much more generous than theory. What I mean with that, the theory works because of the fixed point theory. Finally, one is able to prove things for sufficiently small data, right? But when we do the numerical experiment, we don't care much about that, and we just run any experiment, and we don't check those smallness assumptions because it depends on constants which are unknown, constants that come through the analysis. But the numerical experiment, as I mentioned here, are much more generous than theory. And even, remember the first example that in 2D, the discrete analysis was depending on the fact that one projector was bounded. We were able to prove it only in 2D. In 3D, in 3D, there is no proof for that. But still the numerical experiment in 3D worked perfectly. So, and open problems, well, here I'm saying, avoid or diminish the smallness data assumptions and stability of orthogonal projector in 3D. I will just mention. And now I finish, Lucas. Related works concerning these ideas, for Businek problem, we also obtain, it is also obtained that. For the stationary Navier-Stokes problem, for the steady-state model of fluid cell bed, is a joint work that we did with Yuri. For the stress-assisted diffusion problem, it's also possible to obtain that formulation for nonlinear transport. Also, we obtained that. So thank you very much for your attention, and that's.
All right. Thank you very much, Gabriel, for this very nice talk and all these very nice, powerful results that you've shown us. So do we have questions, comments, concerns, ideas, suggestions, criticisms, jokes? Well, I'll start with a quick question then. Gabriel, you mentioned at some point that you needed the Neumann problem to get through the analysis and eventually prove existence and unicity of your solutions. And when you bring the Neumann problem, there are restrictions for the ranges of the exponents of the spaces. So it might be, I think you mentioned on your final slide, that it might be that the physics does not allow you to do that.
Maybe, yeah.
So what happens? What do you do in those cases? Is it a technical problem that does not allow you to carry on with this kind of analysis? Or is there an essential problem on the physical model?
I actually don't know about the physical model much, but I will say that we used a result given the existence of a solution for a normal problem, and which shows that far from, outside that range, there is no solution. So it is a technical result that allows us to use that in that specific range. And it is proved by the people who did it that outside that range, there is no solution. So doing it in this way, we are somehow stuck to that ranges. But still, as I said, the numerical experiments are right. So are the opposite to the government. You see, government. I mean, to the opposite to the program of the government. They promise a lot of things, but they just do a little. Here is the opposite. We are able to prove a little, and we can do a lot of things numerically.
That's more generous, right?
Bad joke, anyway.
Yep. Do we have other questions, other comments? I'll do another one then, final one. This is a small one, not sure if it's even a good question, so I apologize in advance. So it's a more philosophical question. When you have Navier-Stokes equations and nonlinear terms, the nonlinear terms can become strong. And it depends all on those parameters that you pointed us in your slides. At some points, physics will tell us that there are multiple solutions. You could have two possible solutions for the flow. Where in the analysis would that appear? Is it the loss of ellipticity on the of the bilinear forms that is the symptom of the fact that unicity is lost?
I would say that it will appear first in the derivation of the wave formulation where you handle those terms. But because, as I showed, when you apply the Holder inequality, depending on the power of the nonlinearity you have, you are going to obtain different indexes. So my conjecture will be that you will get trouble first in the definition of the indexes where the unknowns are to be thought. You see, it's and perhaps also in later on in the proofs of some of the IMSAP conditions.
Okay. Very good. Any more questions? I think we should thank Gabriel again for this very nice talk.
Thank you very much.
And if I'm not mistaken, we have coffee break now. Yep, thank you. Thank you very much. Sorry? We have to be back here at 11, okay? Thank you.